We generate petabytes of data every single day. For decades, we have successfully organized this massive digital ocean using traditional relational databases. These systems rely on strict, exact match rules to function. If you type the word apple into a standard SQL database, it dutifully scans rows and columns looking for the exact character string APPLE. That works beautifully for tracking strict inventory, but human language is messy. We communicate using concepts, context, and abstract intent. Imagine a user searching a medical forum for the phrase, "fruit that keeps the doctor away." A traditional database evaluates that query and tries to find a literal match for those exact words. It completely misses the obvious answer, an apple, because the system has no capacity to understand what the words actually mean. As we build advanced artificial intelligence, these rigid text-only systems break down. A modern AI requires an architecture that can comprehend concepts. To bridge the gap between human language and machine logic, we have to translate abstract words into measurable mathematics. Machine learning models translate apple into a vertical array of numbers, a vector embedding. Plotted as coordinates, similar concepts receive similar numbers. Apple and banana plot together. Car sits far away. Exploding into thousands of dimensions, distinct clusters form, creating a dense information web. By converting concepts into coordinates, we have successfully transformed messy, abstract human thought into a structured, searchable mathematical landscape. Now that human intent exists as a web of numbers, how does a computer actually search through this space? A search query drops in, measuring geometric distances. Shorter distance means closer meaning. Measuring billions of points in real time creates an inefficient bottleneck. Approximate Nearest Neighbor algorithms solve this by grouping data into neighborhoods and building structural express lanes, bypassing individual measurements for massive speed. This algorithm is the critical mechanism that makes semantic search possible at an enterprise scale without crashing the system. We see the direct impact of this speed in modern consumer AI. Large language models frequently invent false information, a highly visible problem known as hallucinating. Models hallucinate because they lack reliable long-term memory and cannot securely access private company data. When asked a specific question, they guess based on their initial training. The architectural solution to this guessing game is called Retrieval-Augmented Generation, or RAG. In a RAG pipeline, a user submits a prompt. The vector database searches its index to isolate and extract the most relevant files. These documents are fed directly into the AI, providing verified context before generating a factual response. By providing the specific documents a model needs to stay accurate, the vector database acts as the literal evidence layer for the generation process. Because this system maps semantic relationships so quickly, it actively powers the product recommendation engines on major retail platforms. Financial institutions rely on this spatial logic to detect anomalies and flag credit card fraud. We even use it to search across different media formats, successfully matching an image of a sunset to an audio file of ocean waves. We have evolved past matching literal characters on a screen. We now map, measure, and retrieve abstract human intent. This shift toward vector-based retrieval provides the foundational long-term memory for the future of artificial intelligence.